Okay, well, this is my first online lecture from Chapter 5, Light the Cosmic Messenger. So, this is my favorite chapter because there's just so much information packed into light. We take it for granted, but it is really our only source of exploring the cosmos. So, in this chapter, we will learn just a little bit of how astronomers, not only astronomers, but from many branches of science, physics and chemistry and so forth, exploit light to probe the world around us. So the first image is, I have an idea of what this is. I mean, it looks like a rainbow with a bunch of black lines in it. This is actually the light from the sun, and you pass it through a very fine prism, not really a prism, diffraction grating probably, but the same thing. It's splitting the light up into its constituent colors. And you may have seen white light go through a prism and split into a rainbow like colors, but you've probably never seen these little black lines, which are really important when we start analyzing the attributes of this light and what it tells us about the sun, for example. I mean, we can do this for other objects as well. This just happens to be light collected from the sun. So by analyzing the patterns we see in this light, we can tell things like how hot the sun is, where its energy comes from, what it's made out of. I mean, tons of stuff. How old it is. I mean, tons of stuff is packed into this spectrum of light. If you're wondering what, if you're having trouble visualizing this, think about just light going into a prism and splitting into like a rectangular rainbow array, but it's split so much that we have to chop it into a bunch of lines and stack them on top of each other. So that's how this square image is collected. Okay, I want to play for you. Oops. Video by Richard Feynman talking about light. Maybe. There we go.
If I'm sitting next to a swimming pool and somebody died,
Of course.
so I can think of something else. I think of the waves, these things that have formed in the water. And when there's lots of people have dived in the pool, there's a very great choppiness of all these waves all over the water. And to think that it's possible, maybe, that in those waves is a clue as to what's happening in the pool. That some sort of insect or something with sufficient cleverness could sit in the corner of the pool and just be disturbed by the waves, and by the nature of the irregularities and bumping of the waves, have figured out who jumped in, where and when, and what's happening all over the pool. And that's what we're doing when we're looking at something. The light that comes out is waves, just like in the swimming pool, except in 3 dimensions instead of the 2 dimensions of the pool. They're going in all directions. And we have an 1/8 of an inch black hole into which these things go, which is particularly sensitive to the parts of the waves that are coming in a particular direction. It's not particularly sensitive when they're coming in at the wrong angle, which you say is from the corner of our eye. And if we want to get more information in the corner of our eye, we swivel this ball about so that the hole will move from place to place. Then it's quite wonderful that we can figure out so easy. That's really because the light waves are easier than the waves in the water are a little bit more complicated. It would have been harder for the bug than for us, but it's the same idea, to figure out what the thing is that we're looking at a distance. And it's kind of incredible because when I'm looking at you, someone standing to my left can see somebody who's standing at my right. That is, the light could be going right across this way. The waves are going this way. The waves are going this way. The waves are going this way. It's just a complete network. Now, it's easy to think of them as arrows passing each other, but that's not the way it is, because all it is something shaking. It's called the electric field, but we don't have to bother with what it is. It's just like the water height is going up and down. So there's some quantities shaking about here, And in a combination of motions that's so elaborate and complicated that net result is to produce an influence which makes me see you at the same time completely undisturbed by the fact that there are influences that represent the other guy seeing him on this side. So that there's this tremendous mess of waves all over in space, which is the light bouncing around the room and going from one thing to the other. Because, of course, most of the room doesn't have eighth-inch black holes. It's not interested in that light, but the light's there anyway. I mean, it bounces off this and it bounces off that, and all this is going on, and yet we can sort it out with this instrument. But beside all that, you see, those waves that I was talking about in the water, maybe they're so big, some of them, and then you could have slower swashes, which are longer and shorter. And perhaps our animal who's making his study is only using waves between this length and that length. So it turns out that the eye is only using waves between this length and that length, except those two lengths are 100,000ths of an inch. 100,000 of an inch big. And what about the slower swashes, the waves that go more slowly, that have a longer distance from crest to trough? Those represent heat. We feel those, but our eye doesn't see them focused very well. We don't, in fact, at all. The shorter waves are blue, the light, and the longer waves are red. But when it gets longer than that, we call it infrared. All this is in there at the same time. That's the heat. Pit vipers they got down here in the desert, they have a little thing that they can see the longer waves and pick out mice, which are radiating their heat, their longer waves, by their body heat, by looking at them with this eye, which is the pit of the pit viper. But we aren't able to do that. And then these waves get longer and longer, and all through the same space, all these things are going on at the same time, so that in this space, there's not only my vision of you, but information from Moscow radio that's being broadcast at the present moment, and the seeing of somebody from Peru. All the radio waves are just the same kind of waves, only longer waves. And there's the radar from the airplane, which is looking at the ground to figure out where it is, which is coming through this room at the same time. Plus the X-rays, cosmic rays, and all these other things, which are the same kind of waves, exactly the same waves, but shorter, faster, or longer, slower. It's exactly the same thing. So this big field, this area of irregular motions of this electric field, this vibration, contains this tremendous information, and it's all really there. That's what gets you. If you don't believe it, then you pick a piece of wire and connect it to a box. And in the wire, the electrons will be pushed back and forth by this electric field, sloshing just at the right speed for a certain kind of long waves. And you turn some knobs on the box to get the sloshing just right, and you hear Radio Moscow. Though you know that it was there. How else did it get there? It was there all the time. It's only when you turn on the radio that you notice it. But that all these things are going through the room at the same time, which everybody knows. But you got to stop and think about it to really get the pleasure about the complexity, the inconceivable nature of nature.
In January 1986, the space shuttle...
And so that's pretty much a complete description, as complete as you can get in 5 minutes, from Richard Feynman. So let's break it down into a little bit more detail, go piece by piece. So this first section is called Light in Everyday Life, and we are going to talk about how we experience light and how light and matter interact. So you feel warm when you walk out into the sun. That should tell you that light is some form of energy. We're receiving energy from the sun in the form of light. I mean, that's the only way the sun's energy could get to Earth. There's a vacuum in space. It's not like the heat is radiating outward like it would be in your oven. Your oven heats largely due to convection cycles of air through the oven. And if you have a convection oven, it's called that because it has a fan that circulates the air around. Well, there's no hot air coming from the sun all the way to reach the Earth. It reaches us in the form of light. And we can measure the flow of energy in light in units of watts. 1 watt is 1 joule per second. So a joule is a unit of energy. Joules per second as a measure of the transfer of energy transfer per time. So we talked about at the beginning that white light is made up of all the colors of the rainbow. White comes in, you get, was it red, orange, yellow, indigo, red, orange, yellow, green, blue, indigo, violet. 7 colors of the rainbow. So 7 colors. So white light is represented by 7 colors. Now the question may be that you may be asking yourself is, why 7? Are there really 7? What's the boundary between these colors? It's arbitrary. Why are there 7? Because Isaac Newton said there were 7. Why did he think there were 7? Well, because you may remember from your religion classes that 7 is one of the perfect numbers in the Bible, but 40 is another. So Isaac Newton had a very strong interest in religion, to say the least. And so since he was the one who discovered the constituents of white light, he said, I'm going to divide it up into 7 colors. That's why sometimes it feels kind of forced, like what's the difference between indigo and violet? The difference is Newton needed 7, so he drew a line and said there's a difference between indigo and violet. So how do light and matter interact? Well, light can be emitted, it can be absorbed, or it can be transmitted. So transparent objects transmit light. Opaque objects block light, they absorb it. And also light can be reflected or scattering. And of course, we're going to go into more detail these things. So this picture here is kind of interesting because it shows you all the different things going on at the same time. So the sun emits light. It absorbs some of that light, mostly in the infrared, which is why it can melt. But it scatters most of the light. That's why snow is so bright and you have to wear sunglasses if you're out skiing or something. By the way, we will talk more about climate later on. So there's a concept called albedo, which is just the reflective nature of an object. How much light does it absorb? How much does it reflect? And so part of the problem we're encountering right now is the Earth is starting to absorb more light than it usually does because a lot of the snow is melting. So the hotter the Earth gets, the more snow melts. The more snow melts, the less light is reflected. And so the waters in the ocean can absorb way more light than ice, floating on top of the ocean would absorb. So therefore things get hotter. When things get hotter, more snow melts, more ice melts, and the rate at which energy absorbed increases. So it's kind of what we call a feedback loop. So the changes start happening faster and faster. Anyway, some other interactions. You see a green tree. The reason it's green is because the red and blue light coming from the sun has been absorbed, and the green is reflected towards us. If you ever try to grow something indoors using grow lights, as they're called, it's kind of weird to be in them because the lights are blue and red, and you think that that's kind of weird. So the plants don't look as green as they normally do. Well, that's because we're not using energy to shine green light on a plant when it's just going to be reflected by the chlorophyll. So instead, we shine on the plant red and blue, which it gets absorbed and turned into sugars. So the glass here transmits light, visible light that is. The glass absorbed most UV light. So if you have the transitions lenses like I'm wearing here, those photochromatic lenses, you're out in the sun, they turn dark, but when you're in a car driving and the sun's beating down on you, your glasses don't turn dark because the sun's windshield absorbs most of that UV light. But the visible light passes through. The chair looks red because it scatters red light and absorbs everything else. Mirrors reflect most all colors of the visible light, so you see a reflection of what's around it. And visions created by special cells in your eyes that absorb a very tiny part of the light spectrum. We have two types of emitters. Well, they're both functioning the same kind of way. We've got the sun and this light bulb. If this happens to be an incandescent light bulb, it's emitting light by nature of being hot. We call that black body radiation, and we've got a whole section on that. And the sun, similar thing. So because it's emitting light by nature of being hot, we can analyze that light and say, well, how hot is it? The sun is somewhere around 5,000 Kelvin or so. So 5,000 Kelvin, just subtract 273 and you get degrees Celsius. In Fahrenheit, I don't know, that's what, 8,000 degrees Fahrenheit? Well, the temperature of the filament in the incandescent light bulb is not a whole lot different. We're talking like 2,700 Kelvin. So it's a little bit lower, but it's still thousands of degrees, either Celsius or Fahrenheit. We're talking thousands of degrees. So this light bulb would be lighting your house with heat. More on that a little bit later, but this is why you don't want to have incandescent light bulbs in your house. We have better alternatives now. So reflection and scattering. We've got two different types of. They're both really scattering, but there are two types. If light is reflected, we would say that's specular. Excuse me. If light. So we can say that light can be either reflected or scattered. So light bouncing off of a mirror, is reflected. We're kind of used to that idea. Light comes in, if we think about a ray of light, it can come in at one angle and it will leave at the exact same angle. Scattering, a little bit different. Light comes in and then it bounces back into many different angles. And so what is the difference? What causes the difference between the two types of interactions, reflecting and scattering? Well, it depends on the defects on the surface. If the defects are much smaller than the wavelength, more on wavelength in a second, but if the defects are much smaller than the wavelength of light, light experiences a very smooth surface and it bounces off at the same angle that it came in at. If the defects are large, so think about a projector screen, you can feel it. It feels rough. It has dimples in it. That means the light is going to bounce off in many different directions, which is what you want for a reflector, a projector screen, because you want all the people in the audience here to be able to see the screen, what's happening on the screen. The only way that can happen is if light is bouncing off in many, many different directions. If you were to have a mirror up front, then the whole movie would only be able to be viewed by one person in the audience. That wouldn't be very, very beneficial. So why is a rose red? Well, it doesn't absorb red light. If it did that, you wouldn't see any red light, so it wouldn't look red. If it transmitted red light, well then that would all go through, like same thing. The rose emits red light? Well, no, because specific processes lead to the emission of light, and so none of those are happening with the rose. The rose reflects red light, yes, and it absorbs the others, the other types of light. So summing everything up, light's a form of energy. Light comes in many colors that combine to form white light. And light and matter can matter can emit light, absorb light, transmit light, and reflect or scatter light. Interactions between light and matter determine the appearance of things we see. So let's talk a little bit more about specific properties of light and what causes all these, the properties of light are what leads to these interactions we spoke of. And in order to do that, we'll have to talk about the electromagnetic spectrum. So what is light? That's a question that people fought about for 400 years. Isaac Newton thought light was a stream of particles, and there are certain interactions with matter that can be best modeled by a stream of particles. Huygens and some other people argued that light was a wave, a kind of periodic floppy disturbance type thing. Waves are kind of hard to conceptualize. But around the mid 19th century, when classical electrodynamics theories were being established by Faraday and Maxwell and others, well, let's go into Maxwell for a second. Maxwell started looking at, he developed these equations that described how electric and magnetic fields behaved, and he started playing around with them and said, what if we look at a changing electric field that causes a changing magnetic field that causes a changing electric field? So the result of this would be some kind of a wave, and when he looked at the propagation speed of that wave, calculated it out, the result was very close to what had previously been measured as the speed of light. So that was the first aha moment that said light is a wave. So everything came from there. This was mid 19th century. Wireless communications came 50 years later or so, based on these ideas. And so by the turn of the 20th century, light was a wave. And then the story changed again because with the new physics that was being developed to describe what was happening on the atomic and molecular level, this wave picture of light didn't quite work. But the particle nature didn't quite work either. So they developed this idea of the wave-particle duality of light. It can behave like a wave and like a particle at the same time. It depends on what question you ask. If you want to ask a question about interference, that's more of a wave-like phenomenon, you model light as a wave. If you want to look at some other properties, you would treat light as a particle. When we talk about energy, we talk about photons, particles of light. So we have to keep in our mind this dual nature, and it doesn't make sense. I get that. But as Feynman himself once described this, and actually I'll play a video for you in a minute where he does so. He says, no one really understands this. Because if you mean by understand, relate this to some everyday experience, well, no, we're not atoms, we're not molecules, we're not moving at the speed of light. This is outside of our realm of understanding. All we can do is devise the mathematical relations and test them with experimentation. So let's run back through it. A wave is a pattern of motion that can carry energy without carrying matter along with it. It's kind of hard to conceptualize, but think about throwing a rock into a pond. The waves travel outward. It's just this disturbance in the water that goes up and down. There's no material necessarily flowing. It is just the wave is this disturbance in the water moving up and down. Now, the weird thing about light is it doesn't actually require a medium such as water or air. Sound is a pressure wave, this regular periodic disturbance that travels through the air. You need air to have sound. You need water to have this kind of water wave with the pebble. Light is very different. You don't need a medium. People thought in the turn of the 20th century that there was some kind of invisible medium that permeated all of the universe, and light was a disturbance in that medium. That was just very famously disproven. So we can talk about certain properties of the wave being the wavelength and the frequency. The wavelength is the difference, the distance from crest to crest or trough to trough. So in other words, how long does it take for the disturbance to go all the way down and come back up and be back at the same location? So that's the wavelength. Very long wavelength stuff is radio waves. Very short wavelength stuff is like gamma rays and so on. The frequency is the number of complete oscillations per unit time. So the frequency of 1, talk about the units in a second, but a frequency of 1 means 1 complete cycle in 1 second. The propagation speed of light, or most waves, is fixed. So the speed of light is fixed, but the frequency describes that in this propagation, how many oscillations up and down per unit time do you see? So when we talk about light as a wave of what? What is the disturbance? Well, the disturbance is in the electric field. Let's not go too deep into electric field, but a field is I describe the field as a would-be force. It permeates around a charged particle. So if you have an electric field, then you would have a force if you put another charge in that field. So think about an electron, since I'm a negatively charged particle. When electromagnetic wave interacts with that electron, there's an electric field that first starts pushing the electron up, then changes direction and pushes the electron down, and then repeats over and over again. So when light interacts with that electron, the electron jiggles up and down. So the light wave is a vibration of the electric and also the magnetic fields. Two different phenomena, but they're very closely related. So that's why we refer to light as an electromagnetic wave. And light then interacts with any charged particles. Wavelength and frequency in a little more detail. So this is wavelength of 1 centimeter, it's crest to crest, and a frequency of 30 gigahertz. This is just, don't worry about the scale or something. I'm just comparing these different waves. So if I cut the wavelength in half, I'm squishing the wave down. I'm compressing the wave so that the crests are closer together. Well, if I cut the wavelength in half, I by necessity double the frequency because I've pushed more crests together. If I cut the wavelength to a quarter of the original wavelength, then the frequency quadruples. So there's this inverse relationship between the two. Shorter wavelength equals higher frequency. Larger wavelength equals lower frequency. And the wavelength times the frequency equals the propagation speed of light. And that is a constant. 3 times 10 to the 8th meters per second, or 300,000 kilometers per second. So to put this in symbolic terms, usually we use this Greek letter lambda to represent wavelength and F to represent frequency. Most of the time physicists use the Greek letter nu to represent frequency, but the nu looks like a curvy little V and people always get irritated by that. So in this book and in this class, we're using F for frequency. So lambda times F equals C, which is the symbol we use for speed of light. Particles of light, if we look at the other side of that coin, the particle nature of light, we take those particles and we call them photons. They're packets of energy. Each photon has a wavelength and a frequency, which doesn't make conceptual sense to say a particle has a wavelength or a frequency. How does a particle do that? You have to just go with it. It has wave-like and particle-like properties. And the energy of that photon depends on its frequency and wavelength. So this is the equation that describes that. The energy equals H times F. This is a constant called Planck's constant, just a constant of nature. So the energy is proportional to the frequency. But now you already know that that frequency and wavelength are inversely proportional. So if I were to write this in terms of wavelength, I would say the energy equals hc over lambda, where h is Planck's constant, c is the speed of light, and lambda is the wavelength. So energy is inversely proportional to wavelength and is directly proportional to frequency. So, just summing up what I just talked about, we mentioned this relationship: wavelength times frequency equals the speed of light, which is a constant. And we also mentioned that the energy of a photon equals Planck's constant times the frequency, where this is Planck's constant. So we can say that the energy equals hf or hc over lambda. It's directly proportional to frequency. It's inversely proportional to wavelength. This image has a lot of information on it. So if we look at the whole electromagnetic spectrum from high frequency short wavelength to low frequency large wavelength, I think it's interesting to get a picture of how small the visible range of the electromagnetic spectrum is. Our eye only detects things in this range, this small part of the electromagnetic spectrum. When you flip on the radio, you're detecting these long wavelength, low energy photons, or these low energy, large wavelength waves. Radio waves are the exact same phenomenon as visible light. It's exactly the same. The only thing that makes radio waves different than visible light is, number one, our eyes can't see radio waves, and number two, the wavelength is much larger, smaller, lower energy. Interestingly, we see microwaves are in this portion of the radio region. This is kind of counterintuitive for a lot of people because you put food in a microwave oven and it magically gets hot, and we sometimes refer to it as nuking the food. And so we would expect some like high energy stuff just bombarding this food. Actually, no. It's actually low energy photons that are heating the food. In fact, some people like to say that, oh, the microwaves make your food unhealthy. That's nonsense. The reason is that they don't quite understand the electromagnetic spectrum. So when you talk about gamma rays and X-rays, this is the stuff that causes cancer. This is the stuff that's really dangerous, can kill you immediately in the gamma ray region. So they connect the microwave with this stuff. This is also the radiation given off by radioactive substances, like a nuclear reactor or something. Radioactive elements down here. So people somehow connect a microwave with this stuff, when actually the microwave is more connected with your FM radio than they are with this stuff. They're lower energy photons than visible light. How do they magically make your food hot? Well, we haven't talked about this yet. We'll get into it a few sections later, but water has a specific type of light that it absorbs very readily, and that light is tuned in this microwave region, so you can target the water molecules and heat them up really, really quickly. All these different things interact with matter in different ways. So this stuff can break up atoms and do some dangerous stuff, but it's also blocked fairly easily sometimes. Whereas these types of rays, think about the brick walls of the classroom. The visible light is blocked, but the radio waves get through. That's how you can use your radio inside class. Also, that's how you can use your cell phones inside the classroom. So I know no one would do that during my class, but I think in other classes that are perhaps not as interesting, people are using their cell phones in class. That actually, the cell phones communicate in the microwave region as well. And one of the advantages of that is that light passes through walls and such. Another interesting part of the spectrum is the X-ray region. X-rays pass easily through soft material, soft tissue, and get absorbed by the bones. So that's how you can conduct X-ray images. The term X-ray comes from the fact that when it was first discovered, Röntgen was the guy who discovered this, and he didn't quite know what it was, what to call it, so he just called it X-ray, X being unknown. So that's where that comes from. We've got several sources down here: radar, microwave ovens, radio transmitters. We've talked about that. People is under infrared, which is interesting enough because people are, our bodies are like 100 degrees Fahrenheit. So we're emitting light. Just like I told you, light bulbs emit light because they're hot. People do too. The difference is light bulbs emit in this region and people emit light in the infrared region. That's how some night vision works, by looking at heat. And radioactive elements up here. And you have down at the bottom cosmic sources of various kinds. Radio galaxies, cosmic background, microwave background radiation. This is the remnants of the Big Bang, the creation of the universe. This is a tremendous advance in science when people first detected this, because it was predicted to be detectable. We just didn't have the equipment to do it. What the heck is that? And when people actually did discover this, to the exact calculation of the predictions, it was a great success for the Big Bang Theory. Yeah. So, question here: the higher the photon energy, higher energy, shorter wavelength. Higher energy, higher frequency, but shorter wavelength. So there's another curious aspect of light in that since it's a oscillating electric field, like let's say it's oscillating like this, that has some orientation associated with it. Now some light, like light from a thermal source, be it a light bulb or a star, we say it's unpolarized because it just has oscillating fields in all directions, maybe traveling towards you, but the field is oscillating here, it's oscillating there, all around. But we say light is polarized if it's just an electric field oscillating in this in one particular orientation. And the magnetic field, let's say the electric field is oscillating like this, the magnetic field is oscillating perpendicularly to that electric field. Lots of things change the polarization, like reflection off of certain surfaces will change that, and that resulting polarization will give you some idea about the orientation of the surface. Polarized sunglasses, which I'm sure you've experienced, they reduce the amount of light reaching your eyes by polarizing the light coming in. Now, what's the point of polarized sunglasses? Because some glasses are not polarized; they just absorb a certain amount of all light. Well, the idea here is that when the sunlight, which is unpolarized, bounces off the horizontal road, creating glare, that glare then becomes polarized in the horizontal direction because the road is horizontal. So if you wear polarized sunglasses and you orient the polarization just right of the sunglasses, you'll eliminate a little bit of all light, but you will preferentially eliminate that glaring light off the horizontal surface. So the idea is to reduce the light reaching your eye, but reduce more of the glare than everything else. So target that glare. That's what polarized sunglasses do. So it takes unpolarized light, which is an electric field oscillating in many directions, and reduces it to an electric field just oscillating up and down in one direction. So summing up, what is light? Light can behave like either a wave or a particle. Is a vibration of electric and magnetic fields. Light waves have a wavelength and a frequency. Photons then are what we call particles of light. The electromagnetic spectrum. Human eye can only cannot see most forms of light. We just see a small window. The entire range of wavelengths is known as the electromagnetic spectrum.